All right, hello everyone. Thank you again for coming to CCTP3. What I want to do in this talk is I want to describe to you why I think the nearest planet in the universe is really interesting to think about in the context of comparative planetology. You heard about some of these points from Robin's previous talk, and I just want to reiterate these points. I was asked to give a talk here by VEXAG, the Venus Exploration Analysis Group. And so what I want to do is really give a top-level overview of the story of why I think Venus is really, really critical to include in these conversations. Now, Venus might seem like a weird world to think about in the context of habitability if you're not a person who thinks about Venus a lot. And it probably seems like a very, very weird world to think about in the context of planetary biosignatures, given that Venus is a place that's totally uninhabitable and has no life as we know of. Right? It's got a surface temperature of about 740 degrees Kelvin, which is hot enough to melt lead. So you're certainly not going to want to hang out on the surface of Venus. The beautiful yellow clouds are made of a concentrated solution of water and sulfuric acid. They're about 75 to 85% sulfuric acid by weight, so not very friendly. The surface environment of Venus is so desiccated that there's only about 30 parts per million of water vapor in the near surface environment. And so taking all of this together, that paints a very nasty picture. And perhaps it's unsurprising that there's no evidence for life as far as we know on Venus. But despite these major differences, there are some similarities, some broad similarities between these two worlds. These two planets are often called sister planets because they have a similar size, mass, density, and bulk composition. And some researchers believe that Venus may have been habitable in the distant past. And this is still a controversial idea, and this is still an idea that we need more data to really understand if this is possible. But I think it's worth thinking about because the idea that our solar system may have had more than one habitable planet early in its history is a pretty breathtaking concept when we think about the possibilities that get opened up from that. So the story, if you're not familiar with it, goes something like this. So in the distant past, our sun was dimmer. The sun gets about 6% more luminous every billion years thanks to normal stellar evolution processes. And that may have enabled early habitability on Venus, but over time, as the sun got brighter and brighter and brighter, that spelled Venus's doom because eventually it became too hot to support habitable conditions. And so these potential ancient seas that Venus may have had in the distant past would have started to massively evaporate in this picture, leaving behind a desiccated surface environment and an atmosphere rich in water vapor. And as Robin described to you, when you have this very wet, hot atmosphere, you can lift your atmospheric cold trap where water would otherwise condense and rain back to the planet's surface. And that water becomes vulnerable to photodissociation in the upper atmosphere. And that hydrogen can easily be lost to space. But the heavier deuterium, so heavy hydrogen, is a little bit more robust just because it's a little heavier, so it'll tend to stick around. And people have pointed to the fact that Venus has this elevated D to H ratio of about 150 times that of Earth's atmosphere as evidence for this early water loss. For example, Donahue and Russell have suggested that based on Venus's D to H ratio, it may have had somewhere between like 400 to 500 meters of liquid water if that water was spread all over the surface. And this is a really, lovely picture and a lovely story, but is it true? Did Venus actually have habitable conditions early on? Certainly not all studies agree with this. Some studies have pointed to other mechanisms that could produce elevated D to H ratios. For instance, Dave Grinspoon has talked about, cometary impacts impacting Venus and changing the D to H ratio, or outgassing from a fractionated mantle changing the D to H ratio. And some studies like Hamano et al. 2013 have suggested that Venus lost most of its volatiles, very early on in its history in the first 100 million years during the magma ocean phase. We really need more data if we want to understand what the early state of Venus was like. It's possible, we don't know yet, but it's possible that there may be more data that might say some things about the early state of Venus on Venus's surface if we could actually go there and sample the in situ environment. Now, frustratingly, some studies have shown that the surface environment of Venus is mostly only about 800 million years old. And so that becomes very frustrating when you want to search for areas that might be older and have older, potentially samples of this ancient crust that may have been from a more habitable conditions. There are some regions on Venus called tessera that some authors believe are actually older than the surrounding terrains. So these are elevated highland plateaus that are extremely deformed. And some people believe that the tessera are older and might represent more ancient materials that one could perhaps sample and search for ancient evidence of perhaps continent building processes or other processes that may suggest an earlier habitable Venus. What I think is really exciting about Venus is that Venus teaches us about planetary habitability as a planetary process rather than a static state or a static property that planets have over their entire histories. If Venus was once habitable and then lost its habitability, it tells us a really interesting and compelling story about the life and death of a habitable planet. And turning back to our own Earth, as we look towards the future, the sun is going to keep getting brighter and brighter over time. So you can kind of think of Venus as like a magic mirror that reflects the future history of Earth back to forward-thinking observers. And Wolf and Toon have suggested that the conditions needed to push Earth into a Venus-like state may be about 2 billion years into our planet's future. So besides the early, fainter young sun, are there other physical processes that could help to enable Venus's early habitability? And the answer is yes. And one of those processes that Mike Way has done some work on and may talk about later on in this session is the fact that Venus rotates really slowly, and that rotation rate actually impacts Venus's climate. So its rotation rate is about 243 Earth days, which Venus scientists love to point out is longer than a Venusian year. Venus has a really weird rotation. It actually also rotates backwards compared to the other planets. Mike Way's done some work, this is from a 2016 paper, showing that for these very slow rotators, you can generate very, very vigorous convection on the substellar point of these planets, generating very, very thick high albedo clouds on the day sides of these worlds. And these very thick high albedo clouds can actually lower the surface temperature of these planets sufficiently that you might be able to support habitable conditions for billions of years. And people have also thought about slow rotation in the context of exoplanets. For planets orbiting in the habitable zones of M-dwarfs, tidal forces are likely to force these worlds into synchronous rotation, where they spin around once on their axis, once every time they go around their star, similar to what the moon does around Earth. And for these slowly rotating exoplanets, a number of studies have thought about the implications of these slower rotations for these planets' climates. So what's interesting here is that we can learn from Venus about processes that may shape climates on exoplanets. And by observing exoplanets, they may actually show us some of these processes that may have shaped the climate of Venus in the past. You might imagine we could observe planets that are undergoing the transition between habitable states and non-habitable states. We might see planets that are, in the midst of going through a moist greenhouse or a runaway greenhouse. Or we may see planets who have slow rotations and bright clouds on their day side, enabling habitability on them. Now, going back to Venus, when it may have lost a lot of water, as Robin alluded to in his previous talk, when you do that, you can generate a lot of oxygen in your planet's atmosphere. And oxygen is a biosignature that we're going to be seeking in exoplanet atmospheres for, evidence of life. Now, it's possible that the surface and mantle could absorb that oxygen inventory depending on how much you start with. But studies have thought about this in the context of exoplanets and accumulating these abiotic oxygen atmospheres, even for planets in the habitable zone. And this is a disturbing prospect because we don't want to be fooled by abiotic oxygen when we're searching for signs of life in the atmospheres of exoplanets. Glenn Collinson has performed a recent study looking at one way that you can actually lose oxygen, not just through surface reaction processes, but through top of the atmosphere processes. So Glenn had this really cool finding recently of what they call the electric wind, which is this strong, unexpectedly strong electric field surrounding Venus. And it's unclear why Venus has this unexpectedly strong field. It may be due to the fact that Venus is closer to the sun than Earth, so it receives more ionizing radiation from the sun. But what they found that's really cool is this quote-unquote electric wind is strong enough that you can actually even strip heavy ions like oxygen to space. And so this may have played a role in the past, stripping oxygen from Venus's atmosphere if it did undergo massive water loss. And it may play a role on exoplanets. So exoplanets orbiting M-dwarf stars are going to be orbiting quite if they're in the habitable zone, would be quite close to their stars. And these low mass M dwarfs are very active stars. They produce a lot of radiation. And so these kinds of loss processes may be important for thinking about, bias signature false positives around these stars and maybe atmospheric loss processes more generally. So I think it's interesting to think about what Venus can teach us in the context of these biosignature false positives, especially since we think Venus lost a lot of water and yet it doesn't have a lot of oxygen in its atmosphere today. So just to summarize, I think Venus is really crucial to think about in the context of comparative climatology of terrestrial planets. Hey, that's the name of our meeting, because of the fact that Venus tells us this really compelling story of what happens to planets over time and how habitability is a sort of a fragile thing that planets can lose. And then the exoplanets may be able to show us states that occurred in our solar system in the distant past and teach us about processes that operated on terrestrial planets in the solar system in the past. This microphone keeps popping at me. And just a plug for a chapter that I wrote with Stephen Kane in this upcoming title in the Space Science series called Planetary Astrobiology that's coming out next year if you want to know more about these topics. And putting on my editor hat for this volume, if you still owe us your chapter, please get those in. All right, and if I have any time, I will take questions now.
Yes, we have a few minutes for questions. Oh, just a comment. Titan's atmosphere today is very much like the Venus in the past and the Earth in the future, in that the cold trap is leaky. So we have a couple of % of methane in the atmosphere, and that's being photolyzed. So we have a very nice portfolio of examples showing this sort of evolution. Which I think you brought out very well.
That's a great comment. And I think it's really nice to think also about Titan, which is such a different world in this context.
What would be the data that you would need to tell if Venus ever had a liquid ocean or not? So if you could fly one of the Mars rovers onto the surface of Venus, would that be enough? Or
wouldn't that be wonderful? I'm not a geologist, and I would love if there's geologists in the room, if they knew the answer to that question. I mean, I know people have thought about searching for more felsic minerals on Venus' surface that might imply ancient continent building processes, which might require liquid water in order for those processes to operate. I don't know enough to know how well these materials will survive over time if you were to, say, have aqueous alteration of some mineral, and then could you ever see that? I know Colin's wanting to say something.
Yeah, I would go look in the terrasa. I would go look in the most folded terrain you have, where if there were aqueous sediments laid down at any point, you should still have them. If they're only 1 billion or so years old, they might look reasonably good. If they're 4 billion years old, then they're going to be just as cooked as all the Paleoarchean sediments here, so we may be in trouble. But I just go look at the sedimentary geology in the terrasa. Send some gnarly old geologists like Paul Hoffman there.
I'm not a geologist, but the tessera seems to be what a lot of people are interested in. It's folded terrains.
I would just say the problem with the terrastra is, of course, that they are very folded and very chaotic, and finding a landing site there is extremely difficult. We discussed this with the Russians last year at a meeting that many people here are at, and we need very high resolution radar data first to see where we can get down to land something, because if it's more than 15 degrees, these things will topple over and never make it. That's key first. We need super high resolution data to find out where we can put these things down. That's really the key to it, I say.
Yeah. Venus is not easy to visit, but hopefully you'll think it's worth it. Hopefully I agree.
In the role of the oxygen ion escape due to the electric wind, how does that depend on the spectral dependence of the, like, say, the far versus near UV And would that maybe affect the loss rates even more?
Yeah, I think that's a phenomenal question. And I think there's so much work that needs to be done right now to understand what exactly is causing the strong electric wind on Venus. It's not completely clear why Venus has this very unexpectedly strong field. So I would love to chat with you more about that later, especially in the context of exoplanets.